In the preceding lecture, we have introduced the concept of a relation, and we have presented a few properties that particular relations may or may not have. In this lecture, we shall, by way of example, define and study the relation is equivalent modulo 5 on integers, and we shall prove that it is indeed an equivalence. We define a binary relation on the set of integers, denoted by this triple bar with a subscript 5, by stating that two integers x and y are related according to this relation, if and only if their difference is a multiple of 5. To better understand this relation, let us consider a few examples. 5 is equivalent to 0 modulo 5, since 5 minus 0 is equal to 5, and 5 is clearly a multiple of 5. Also, 2 is equivalent to 17 modulo 5, since 2 minus 17 is equal to minus 15, which is a multiple of 5. On the other hand, 5 is not equivalent to 1 modulo 5, since 5 minus 1 is 4, and 4 is not a multiple of 5. And modulo 5, 2 is not equivalent to 26, since 2 minus 26 is minus 24, which is not a multiple of 5. We now wish to prove that equivalence modulo 5 is an equivalence on the set of integers. And because we want to root our arguments firmly into mathematics that everybody knows and understands, let's first formalize being a multiple of 5 in terms of multiplication. Note that x minus y is a multiple of 5 if and only if there exists an integer k, such that x minus y is k times 5. Now we will proceed to prove that equivalence modulo 5 is indeed an equivalence using this alternative formulation of the definition. Note that we now need to prove that this relation is reflexive, symmetric, and transitive. We start with reflexivity. Recall that a relation is reflexive if every element is related to itself. Since our goal is to establish a universal quantification, we declare an integer variable x and set as our new goal to prove that this x is equivalent to itself modulo 5. We now use the definition of equivalence modulo 5 to better understand what this means. The definition tells us that in order to prove that x is equivalent to itself modulo 5, we need to establish a certain existential quantification. Note that here we have simply instantiated the definition of equivalence modulo 5. To prove the existential quantification, it suffices to find some integer k, such that x minus x is k times 5. Let's do some mathematical reasoning. We start to calculate with x minus x, which is of course 0. And since 0 is 0 times 5, and 0 is an integer, we have now found an appropriate witness for the existential quantification. Thereby, the derivation is complete. Let's now proceed and turn this derivation into a more readable textual version of the argument. Our goal is to prove that equivalence modulo 5 is reflexive. To this end, we let x be an integer and establish that x is equivalent to itself modulo 5. We then observe that x minus x is 0 times 5, and 0 is an integer. Thus, we have proved that there exists an integer k such that x minus x is k times 5, which, by the definition of equivalence modulo 5, is enough to conclude that x is equivalent to itself modulo 5. We have first constructed a complete derivation for the formula that expresses that equivalence modulo 5 is reflexive, and then we have translated it into a convincing, readable argument. It pays off to study the text of the argument carefully. Note the use of words such as let, which introduces a variable, we need to establish, which states a new goal in the proof, and so, hence, we conclude, which are all used to announce a valid statement that follows logically from preceding valid statements. Our next goal is to prove that equivalence modulo 5 is symmetric. Recall that the relation is symmetric if for all elements x and y, whenever x is related to y, then also y is related to x. Our goal is to establish a universally quantified implication. So we declare integer variables x and y, assume that x is equivalent to y modulo 5, and set as our new goal to prove that then also y is equivalent to x modulo 5. Let's first apply the definition of equivalence modulo 5 to the assumption. According to the definition, there exists an integer k such that x minus y is k times 5. We can also apply the definition of equivalence modulo 5 to the goal in order to better understand what we should prove. Note that the witness showing that x minus y is a multiple of 5 need not be the same as the witness showing that y minus x is a multiple of 5. It is good practice to already take this into account when we apply the definition of equivalence modulo 5 and rename the bound variable of the existential quantification. We use an L instead of a k. Let us declare the witness of which the existence is implied by the assumption that x is equivalent to y modulo 5. K is the integer satisfying that x minus y is k times 5. Our goal is to find an integer L such that y minus x is L times 5, and we hope that the relation between x, y, and k can be of assistance. So let's do some simple mathematical reasoning starting with y minus x. Note that y minus x can be expressed in terms of x minus y. It is minus x minus y. And then we can use that x minus y is k times 5. With some further standard mathematical reasoning, we find that y minus x is minus k times 5. Moreover, minus k is clearly an integer. So we have now found an appropriate witness for the existential quantification that we needed to prove. Minus k can play the role of L in the existential quantification, for we have shown that it is an integer and that it satisfies y minus x is minus k times 5. The derivation is complete, symmetry is established, but we still want to turn this derivation into a more readable textual version of the argument. Our goal is to prove that equivalence modulo 5 is symmetric. To this end, we let x and y be integers and suppose that modulo 5 x is equivalent to y. We then need to establish that, again, modulo 5, y is also equivalent to x. First, we conclude from the assumption that x is equivalent to y that there exists k such that x minus y is k times 5. Then, by some straightforward mathematical reasoning, we conclude that it follows that y minus x is minus k times 5 and minus k is an integer. And this, in turn, allows us to conclude that there exists an integer L such that y minus x is L times 5. By the definition of equivalence modulo 5, this is enough to conclude that y is equivalent to x modulo 5. We have first constructed a complete derivation for the formula that expresses that equivalence modulo 5 is symmetric, and then we have translated it into a convincing readable argument. Here you see the resulting argument. Again, pay special attention to the use of the phrases let, which introduces a variable, suppose, which introduces an assumption. We need to establish, which states a new goal in the proof, and it follows, then, so, hence, and we conclude, which are all used to announce a valid statement that follows logically from preceding valid statements. These phrases serve to expose the logical structure of the argument. A clearly exposed logical structure is a crucial element of a convincing proof. The last thing we need to do before we can conclude that equivalence modulo 5 is an equivalence relation is to prove that it is transitive. We should establish that for all x, y, and z, if x is related to y and y is related to z, then also x is related to z. Our goal is to establish a universally quantified implication. So we declare integer variables x, y, and z, assume that x is equivalent to y modulo 5 and y is equivalent to z modulo 5, and set as our new goal to prove that then also x is equivalent to z modulo 5. Let's first apply the definition of equivalence modulo 5 to both the assumptions and the goal. Note that we carefully make sure that the bound variables used in the respective existential quantifications are all named differently, to prevent confusion later. Let us declare witnesses for the existential quantifications resulting from the assumptions that, modulo 5, x and y and also y and z are equivalent. In order to prove that there exists an integer m such that x minus z is m times 5, we shall do some mathematical reasoning. It starts with x minus z, which we would like to express in terms of x minus y and y minus z, because of the information we already have about these terms. Note that x minus z is the sum of x minus y and y minus z, And this is the main mathematical insight needed for this proof. For we can now replace x minus y and y minus z by k times 5 and l times 5 respectively. And then rewrite this expression to k plus l times 5. Since k plus l is an integer, and we have just shown that x minus z is k plus l times 5, we have now found an appropriate witness for the existential quantification that we needed to prove. K plus L is apparently fit to play the role of M in the existential quantification. The derivation is complete, proving that equivalence modulo 5 is transitive to those who can read derivations. We still want to turn this derivation into a more readable textual version of the argument. Our goal is to prove that equivalence modulo 5 is transitive. To this end, we let x, y, and z be integers, and suppose that, modulo 5, x is equivalent to y and y is equivalent to z. We then need to establish that, again, modulo 5, x is equivalent to z. First, we conclude from the assumptions regarding x, y, and z that there exist k and l, such that x minus y is k times 5 and y minus z is l times 5. Then, by some straightforward mathematical reasoning, we conclude that it follows that x minus z is k plus l times 5 and k plus l is an integer. And this in turn allows us to conclude that there exists an integer m such that x minus z is m times 5. By the definition of equivalence modulo 5, this is enough to conclude that x is equivalent to z modulo 5. Here you see the resulting textual argument, which should convince everybody with a good understanding of logical reasoning and some modest mathematical training that equivalence modulo 5 is transitive. We have proved that the relation is equivalent modulo 5 is reflexive, symmetric, and transitive. And therefore we may now conclude that equivalence modulo 5 is indeed an equivalence relation. This concludes our discussion of the example relation equivalent modulo 5 on integers. In the next lecture, we shall see that in general, equivalence relations nicely partition the set on which they are defined into classes.